In question number 11, we have been given a spherical shell, and the inner radius of the shell has been given to be r1. So this distance is r1. The outer radius of the shell, that is this distance, has been given to be r2. A charge q has been mentioned to be uniformly distributed in this region. Now there is a point P which I will mark over here. This is point P, and the distance of P from the center of the shell, that is from this point C, in other words length CP, has been given to be x. Notice that r1 is smaller than x, and that is smaller than r2 as mentioned in the question. The question asks us to find what is the electric field E bar at this point, at point P. We begin solving the question by making an assumption, namely we'll assume that Q is positive. Now we will see that this particular assumption does not affect the general nature of the solution. So our solution will also work if Q is negative, but this is a good starting point. Now if you look at the figure and you just imagine that a positive charge is uniformly distributed in this region, then the symmetry of the situation tells us that the electric field at point P must necessarily, if it is non-zero, it must necessarily be in the radial direction, and we'll assume that it's radially outwards. Now this field, let us call it E. So our question is, what is the value of E? Notice that E could be either positive or negative. In other words, although we have drawn an outward pointing arrow, it is possible that the field actually is in the radially inwards direction. So we are trying to generate a very general type of solution. Now the next point we should look at is there any other location in this figure where the electric field has the same magnitude? For example, if I mark a point over here which is at the same distance x, this distance is x, as the point P's distance from C. So both CP and CP dash is equal to x. Now clearly from the symmetry of the situation, the electric field at point P dash will have the same magnitude as that at P, and it will again be radially outwards in the figure, so I mark it as E. In fact, the same condition will prevail at all points in the figure which are at a distance x from point C. Now this gives me a clue as to how to draw the Gaussian surface. What I do is I construct a sphere, and the sphere's center will again be the same point C. In other words, I'm going to construct a Gaussian spherical surface which is concentric with this spherical shell, and I'll just draw it like that. It passes through P, it passes through P dash, and it passes through all of these similarly placed points. So this dotted surface which I've shown is my Gaussian surface. Now I apply Gauss's law to this surface. So according to Gauss's law, the flux which comes out of this surface must be equal to the charge enclosed by it divided by epsilon naught. The left hand side is the flux coming out of the surface, clearly it will be E multiplied by the surface area of the Gaussian sphere which we have drawn, and that's going to be 4 pi x square because its radius is equal to x. And on the right hand side I'll write the enclosed charge, which is q in, the net enclosed charge, divided by epsilon naught. Now the net enclosed charge can be written as the charge density, which I'll write as rho, multiplied by the volume of the region where the charge exists, and of course this I'll divide by epsilon naught. Now let's look at the volume which we are going to substitute over here. Remember, the charge within the Gaussian surface is present not everywhere in the Gaussian surface. For example, there is a hollow spherical region of radius r1 where no charge is present. So essentially what we are doing is we are looking at the charge which is present in this region, which is again a spherical shell of inner radius r1 and outer radius, meaning this distance, x, and it is the volume of the shaded region which I want to substitute over here. So of course this becomes, it's equal to rho multiplied by the volume of the shaded region is clearly 4 upon 3 times pi times x cube minus r1 cube, and this I divide by epsilon naught. Now I will rewrite the equation over here. It's E into 4 pi x square equals, and rho I will now substitute as the total charge q divided by, now the total charge q is contained in the entire spherical shell, that is, it is enclosed between a sphere of radius r1 and a larger sphere of radius r2. So the volume in which q is present is 4 by 3 times pi times r2 cube minus r1 cube. That's the charge density rho. Now of course this is multiplied by 4 upon 3 pi times x cube minus r1 cube, and it's divided by epsilon naught. So we have written the right hand side, and what I can do is I can take this 4 pi x square term down to the denominator in the next step. So I'll just take it down like that, 4 pi x square epsilon naught. So of course one can readily see that the 4 by 3 pi term, it gets cancelled here and here, and what finally remains is E equals q multiplied by x cube minus r1 cube divided by 4 pi epsilon naught x square multiplied by r2 cube minus r1 cube. Now I have transferred some parts of the solution to this new page before we answer the second part of the question, which says we have to draw a graph of E versus x for the range 0 less than x less than 2 times r2. Now remember, if you look at this particular interval from 0 to 2r2, or you could even plot it from 0 less than or equal to x less than or equal to 2r2. Remember, we are starting at the center of the spherical shell, and by the time we reach x is equal to 2r2, we are in the exterior of the shell. So this is a representative interval, and it will tell us more or less what happens in the interior, that is in the hollow, in the shell itself, and in the exterior of the shell. Now to make the question simpler, what we can do is we can divide this interval into three parts. My first part will be the interval 0 less than or equal to x less than or equal to r1. Now when x lies from 0 to r1, we are in the hollow, and at the most one may be at the surface of the hollow. However, one knows by the shell theorem of gravity, which is also applicable in electrostatics, that the electric field in this hollow will be equal to 0. So what we have is E equals 0 for this particular region number 1. The next region, region number 2, which we will be considering, will be the region which satisfies R1 less than x less than or equal to R2. So clearly this is the region which is over here. That is to say, it's the region where the charge is physically located. And clearly in this region, it is this formula which we have derived in the earlier part of the question which is valid. And so I'll rewrite that formula, but I'll write it in a slightly different way. In region 2, E equals, now the Q is a constant, I'll write it separately like that, 4 pi epsilon naught, I'll group it together with Q, all constants I'm grouping together, and R2 cube minus R1 cube is also grouped together. So this is some constant, and now I multiply by the terms which depend on x. So there are two terms, one is in the numerator, x cube minus r1 cube, the second is in the denominator, x square. So for a certain reason I will split that fraction into 2. So what I get is x cube upon x square is x, minus the second term will be r1 cube divided by x square. Now before analyzing this further, I'll just make some place to draw the graph. So I'll just remove this part of the solution, it's not needed anyway. So as you can see, I have drawn the e-axis, the vertical axis, and the horizontal x-axis. Now we'll just mark some points. So this point on the horizontal axis corresponds to x equal to 0, and this point, let us say it corresponds to x equal to r1. This point could be x equal to r2, and we have to go right up till 2r2. So maybe I can mark 2r2 somewhere over here. Now in the first region from 0 right up till r1, the value of E is equal to 0, and so it's going to be, the graph is going to look like this. It's along the horizontal axis like that. Now the next part of the graph I wish to draw corresponds to the region to the right of R1, and it goes up to R2. Now let's see what happens slightly to the right of R1. So essentially what I want to do is to take the limit of this expression as x tends to R1 from the positive side. So if you look at the expression, in the limit I'll be substituting x equal to R1, and here too I'll be substituting x equal to R1. Clearly this entire term, this bracket, is going to cancel because I've got R1 here and R1 cube upon R1 square, so that's also R1. In other words, the limit as x tends to r1 plus of this particular expression is equal to 0. So the limit is equal to 0, and what that essentially means is the function is continuous at x equals r1. So I'm going to start the graph to the right of r1 at this point itself. I don't know what's going to happen. It's going to go up or down or whatever, but it will start at this point. So I'll just rub out whatever I have did right now. That's just a representative graph. It tells you that I want to start at r1, and of course now I want to investigate what happens at x equal to r2. So in this function I'll substitute x equal to r2, and here too I'll substitute x equal to r2. So basically the bracket will become r2 minus r1 cube divided by r2 squared. Now one may see that this reduces to r2 minus r1 upon r2 the whole square. You can write it that way, and multiplied by r1. And clearly this term is less than r2, that's the data, and this term is a fraction. It's from 0 to, that is, it is greater than 0. The term I'm calling f, r1 upon r2 the whole square, and it's less than 1. I called it f because it's a fraction. So what we are doing is multiplying this r1, which is anyway smaller than r2, by a positive fraction which makes it even smaller. So essentially this entire thing, r2 minus this whole thing, in other words this bracket is going to be smaller than r2, that's for sure, but it is also going to be greater than 0. So it's going to be some positive number, and I'm multiplying it by this positive number because remember I've assumed that q is positive, and r2 down here, r2 cube, is greater than r1 cube, so that's also positive. So in short, when I reach x equal to r2, that is in the graph, when I reach x equal to r2, the graph ends up at some positive value of e, and I'll mark that value by this point over here. So the graph has to be drawn from this point to that point, and we are not sure currently whether the graph goes this way or it goes straight or it goes like that. We are not really sure. We have to find that out. Now to do that, I find what is the derivative of this particular function with respect to x. So dE by dx equals, now this first thing, whatever q upon 4 pi epsilon naught r2 cube minus r1 cube, I'll write it as a positive constant k, and I have to multiply this by the derivative of the bracket, which is 1 plus 2 r1 cube divided by x cube. And I know for sure that this particular expression is greater than 0 for the interval of x which we have chosen. Now we can see that as x goes from r1, or a bit larger than r1 actually, because our range, or rather our interval, starts slightly to the right of r1, as it goes from, I'll call that r1 plus, as it goes from r1 plus, as x goes from r1 plus to r2, what happens is the term in the denominator, namely x cube, goes on increasing. So that would mean that this entire fraction, the positive fraction which you're adding to 1, goes on decreasing. Now that would mean that the derivative decreases as x goes from r1 plus to r2. 2, which means that the slope of the graph, although positive, it's going to start at a comparatively large positive value, and it will decrease continuously to a small positive value by the time I reach x equal to r2, and that is going to help us to draw the graph in this particular interval. Remember, I start at r1, I have to start it with a comparatively large slope like that, and I finally, the slope decreases until it decreases to a smaller positive value by the time I reach this point. And now finally we are left with the third region, which of course means the region corresponding to r2 smaller than x smaller than twice r2, but we could even try to imagine the graph right up till x tending to infinity. Now clearly, when we are in this particular region, we are outside the shell, we are in the exterior, and that would mean that we can once again apply the shell theorem, and the entire charge q can be assumed to be located at the center of the shell, and it means it becomes a point charge at the center of the shell located at point C in the figure, and so Coulomb's law becomes applicable. What we do get is therefore the value of E is given by Q upon 4 pi epsilon naught times x square, where x lies in this range, x lies between r2 and infinity, and we know that this type of graph, it goes down like this. That's the general nature of the graph. And we also know that in shell theorem, this is actually shell theorem number 1, the shell theorem number 1 can be applied right up to the surface of the outer sphere. What I mean to say is, if I consider a point right over here on the surface, which is not technically speaking in the exterior of the shell, I still get the same value of the field at this point. I mean, I get it by the same formula, namely q upon 4 pi epsilon naught x square. The formula for the field in the exterior is the same, and the formula for the field on the surface of the shell is also q upon 4 pi epsilon naught x square. In other words, when we draw this graph in the figure, it's going to be continuous at x equal to r2, namely at this particular point. So the general nature of the graph would be something like this in the exterior. It would go down and down and down, and it would eventually be asymptotic to the x-axis. So this in short will be the general nature of the graph. So initially the field is equal to 0, and then as I get into the body of the shell, the field will increase with distance from the center, and finally when I get outside the shell, the field once again decreases and it reaches 0 at x equal to infinity.